All right, let's do some of these area between two curves. Starting with number 7. I'll sketch the region enclosed by the curves and find its area. So I'm good at sketching curves. How about you? I got y equals x squared, and then y equals the square root of x, and x equals, they intersect at 1, and x equals 1/4, and x equals 1. I don't know why they told us x equals 1. That's kind of redundant because we already got an intersection there. So we're talking about this area right here. Okay, so let's see. Who's on top? First of all, if we look as we kind of scroll across this area, we're definitely like going across this way, like our little... this is like, these functions are given in y equals form, which is just to say this is a dx problem. I think in the notes I didn't talk about the what happens when the functions, quote unquote, are given in like x equals, that they're not actually functions, or they're if they are, they're given in that x equals form, and the area is better understood as like a, not who's on top and who's on bottom, but who's to the right and who's to the left. Then it's a dy problem, but we'll burn that bridge when we get to it. So here I've got the integral from 1/4 to 1, and who's on top is the x to the 1/2, and x squared is on the bottom. So antiderivative of x to the 1/2, bump the exponent up 1, and divide by that new exponent. I know how to do calculus. So let's see, plugging 1 to this gives me 2/3 minus 1/3. And plugging 1/4 into this gives me, let's see, the square root of 1/4 is 1/2 to the third power is 1/8 times 2/3 is 1/12 minus 1/4 to the third power is 1/64 over 3 is minus 1 over 1/64 over 3 was 64 times 3 is 192. Just did some math there. So let's see, I got 1/3 minus 1/12 plus 1 over 192. That's got to be the common denominator here, I would think. Well, 64 is the thing there, so that's equal to 64 over 192 minus 12 times 192, say what, 16 times 12 is 192, so minus 16 over 192 plus 1 over 192. 64 minus 16 is 48, plus 1 is 49. Now, if you just got really stressed out about all that math that just happened, a couple things to say. First of all, this is a math class, although we do push symbols around an awful lot. Still need to be able to do math. Second of all, it's actually acceptable to leave your answer like this. Depending on how much, on a scale from 1 to 10, on how obsessive compulsive you are, it would not be possible for me, pretty much, to leave my answer like that. I have to see it through to the end, and I don't mind doing it. So if you're really hyper-allergic to that sort of thing, you can just chill. So let's see, here's the next one. Y equals 0, x equals 0, and x equals 2. I'm not going to write out those equations, so I just need a sketch of this, which I'm just going to factor here because I think that would be instructive. So this is a cubic function that goes -2, 0, 2. It's going to go like this. Oop, no, it's not. Other way, because the leading term, the highest degree term, is positive, which means that it's got to be positive at that end. Right, that's very basic end behavior stuff. Probably you learned that in Algebra 2 or some other silly class like that. So what are the other boundary things? Y equals 0. That's the x-axis. X equals 0, and x equals 2. So we're talking about this right here. Okay? There's a couple ways to think about this. You could think about it as, okay, who's on top? The x-axis, which is y equals 0, is on top, minus x cubed minus 4x. Or you could think about like, oh, I could have just done this in the last chapter thinking about area, because I would have just found this integral and then said, oh, you want the positive version, you make it positive. So either way, since we're thinking about this top minus bottom, I like that approach to it. So let's see. We have minus x cubed, so the antiderivative of that, and then plus 4x, the antiderivative of that would be x squared, 2x squared. And plugging 2 in here, that's minus 16 over 4 plus 2 times 4 minus 0. So that looks like the answer is 4. Number 9, y equals cosine 2x. So what happens to the function, the cosine function, when you put a 2 on the inside? That means the period is 2 pi divided by that 2, so the period is only pi. So it starts here, and it goes all the way through its little cosine dance. Like that. A period of pi. And that's 1 there. So y equals 0. And we want to go from pi over 4 to pi over 2. So this is pi over 2 here, and this would be pi over 4. So we're just looking at that right there. Okay, so let's integral from pi over 4, pi over 2 of the top minus, because that's just the axis on top, minus the bottom, cosine 2x. Let's see, so what is the antiderivative of minus cosine 2x? Antiderivative of minus cosine is minus sine, right? Yeah. And you can just check by taking the derivative of that. And then since there's a 2 inside, you're going to have to be, you need a 1/2 out here. That's that kind of just a multiple of x, so probably you're not going to write out a u substitution for that, since it's just a number times x. You could, but that should be what you end up with. And we'll find out in a sec. We did it right. Now that's a constant, so I'm going to pull that to the outside. So I have the sine of 2x. So that's the sine of pi. The sine of pi is 0 minus the sine of pi over 2. Sine of pi over 2 is 1. So negative 1/2 times negative 1, that's 1/2. And what's the right answer? Number 10. Y equals secant squared. Do you know what that looks like? Well, and where are we going from? negative pi over 4 to pi over 4. So focusing just around here, here's the cosine curve, or part of it, from, that's pi over 2 to negative pi over 2. So secant is 1 over this. So when you try to flip those zeros over, like 1 over 0, that's going to give you asymptotes there. When you flip this 1 over, you just get 1. So that's a graph of the secant function. And when you square these values, when you square 1, you get 1. When you square these big things, you get bigger things. So it just kind of like makes it a little bit steeper. But it looks the same as this. And then pi over 4 is here. So the graph that we're interested in looks kind of like that piece of it. Pi over 4 is only halfway to those asymptotes. So it looks kind of like this. Oh, maybe it doesn't look like that. Hold on, let me look at the defining things. Y equals 2. Oops. So y equals 2 is going to be something that cuts across here. Now, where does that intersect the curve? So 2 equals secant squared x. So that would be that would mean secant would be equal to plus or minus 2. I'm just going to do the square root of 2. I'll put that there, fine. And then that's cosine upside down. So that would be like 1 over the square root of 2, which is the same as square root of 2 over 2. So that happens at plus or minus pi over 4. So it actually does intersect right there at 2. So that's nice. So I shaded in the wrong part there. We could do that, but they're asking us for that area. So, I mean, in the process of doing this, otherwise easy, what's the integral top to bottom? This is a good review of stuff, right? What graphs look like and trig and stuff. All right, so I think we're good there. Oh, no, no, we're not. What's on the top? 2 is on the top, and the secant squared is on the bottom. So that's what I want there. So the antiderivative of 2 is 2x. The antiderivative of secant squared is tangent. That's just a thing that you know, right? That one knows. All right, so let's see. Plugging in the pi over 4, I get 2 times that, which is pi over 2 minus the tangent of pi over 4 minus, I plug in negative, I get negative pi over 2, and then I get minus the tangent of negative pi over 4, which is minus right, which is negative 1. And you might also notice by the symmetry of this graph or the symmetry of these expressions or whatever you want, that what we're just going to end up doubling this. So it's pi, however you scramble all that out there, it's pi minus 2. Number 11, here we go. So here's the ones that are sideways like. So x equals sine y. What does that even look like? Well, it's like the, just like the sine function, except you're plugging in y values and getting the x values, right? So it's the inverse of the sine function. Except we're not fussing about things being inverses, so we're going to let it fail the vertical line test. X equals 0. That's that. Y equals pi over 4. and y equals 3 pi over 4. That's at pi right there. So we're talking about this little jobby here. So this is a not who's on top and who's on bottom, but who's to the right and who's to the left. So we want the integral from pi over 4 to 3 pi over 4. And now notice that our limits, like the a and the b, like from our notes, those are now on the y-axis. I'm going from here to here. And from there to there, the sine function, sine y, is on top, and the axis is on the bottom. This is a dy problem. If you think about what the dx really means, it means like all those little tiny bases of rectangles when we make our Riemann sums. So here we're making the rectangles this way. So those little bases are little dy's. And also this is a y, so better be dy, or you can't do it. What's the antiderivative of sine? It's negative cosine from pi over 4 to 3 pi over 4. That's a negative sign. That's a constant, so I'm going to bring that to the outside and just do the cosine. So cosine of 3 pi over 4. Cosine of 3 pi over 4. If, however you about that, this is pi here. So 3 pi over 4, that's pi over 2, is here, right? So cosine of 3 pi over 4 is the negative square root of 2 over 2. Minus the cosine, remember this minus sign got pulled to the outside by me, cosine of pi over 4 is positive. So that looks like all the negative signs cancel out, and I get 2 of those, so it's just the square root. It's half a square root of 2 and another half square root of 2. It's a square root of 2. If you do something like this and you got your graph and you get 0 here, like that can't possibly be right. Look, like that doesn't have an area of 0. So use some common sense. Like number 12, x squared equals y and x equals y minus 2. Okay, it's kind of weird that they gave those in. I'm gonna write them like this: y equals x squared and y equals x plus 2. I'm just going to rearrange that one, add the 2 to the other side, and make a sketch. So x plus 2, that's okay. So this area here, right, that's a line with y-intercept 2, slope 1. Where do they intersect? Well, they intersect when x squared is equal to x plus 2, or in other words, when x squared minus x minus 2 is equal to 0. And I took algebra once. Such a bummer when you know how to do all the calculus in your algebra. Can't get it done. So it looks like I want the integral from -1 to 2 of who's on top. X plus 2 is on top, minus x squared is on the bottom. All right? So that is antiderivative of x, antiderivative of 2, antiderivative of x squared. All right, looks like we're going to have some fun math to do here. Plugging 2 in here gives me 4. Plugging 2 in here gives me 4. Plugging 2 in here gives me 8/3. Minus. Plugging -1 in here gives me 1/2. Plugging -1 in here gives me -2. Plugging -1 in here gives me, that's -1, so it would be plus 1/3. Right? So I got 4 plus 4. I'm going to leave the fraction part here because I got a good feeling about this. So 4 plus 4, and then I got plus 2 and minus 1/2. So that's 10 minus 1/2, 9.5 or 19/2 would be one way of writing that. And then here I've got minus 8/3 minus 1/3. That's minus 9/3 or minus 3. So that's 6 halves. So that's 13 over 2. Again, if that really stresses you out doing that kind of thing. Wait, what number was that? 12? Hold on. Hold on a second. I don't have the right answer. Dang it. All right, let's just re-examine here for a second. What did I do? Antiderivative is good. Plugging 2 in. Oh, whoops. You know what 4 divided by 2 is? So that's going to make this 2 less, which would make it 15. And then that's 9 halves. So that gets us the right answer. 9 halves is the correct answer. Okay, so anyway, blah, blah, blah. If this really stresses you out, you can leave it like that. That's the short version of me rambling on about it. 13. Y equals e to the x. Y equals e to the 2x. And x equals 0, and x equals natural log 2. Okay, so what do these look like? Well, e to the x looks like this. And we have, what are the, x equals 0, and x equals natural log 2. E to the natural log 2 is 2. And then e to the 2x, well, when x is 0, that's still here. But when you plug in when you plug natural log 2 in here, that's 2 natural log 2, which is the same as natural log 4, so that's going to be up here. So e to the 2x looks something like that. So this area that we're trying to find is this little wedgy thing in here. It is the integral from 0 to natural log 2, and e to the 2x is on top minus e to the x on the bottom. And the antiderivative of e to the 2x is 1/2 e to the 2x, because calculus. Okay, so plugging natural log 2 in here, I get e to the 2 natural log 2, which is the same as natural log 4, so that's 4 times 1/2 is 2, and then minus e to the natural log 2 is 2. Don't really like that, not going to lie. Minus here, when I plug 0 in here, maybe we're okay. So I plug 0 in here, I get 1/2 times e to the 0, so that's 1/2. And then minus e to the 0. So that's, comes out to be positive 1/2. Yeah, that's right. Number 14, 3 more. How about x equals 1 over y, and then I just have straight lines after that, so let's just graph this. This is the inverse function. X equals 1 over y, and y equals 1 over x. Of course, that's the same thing. There is this piece. I have a feeling we're not going to need that. Okay, and then what other boundaries do we have? X equals 0. That's the y-axis. Okay, so that's a boundary. And then y equals 1. That's a boundary. And then y equals e. That's up here somewhere. Okay, so we're talking about this region here after we make that sketch. So this is not a who's on top, who's on bottom. This is a who's. The curve here is on the right, and then that boundary's there. So this needs to be a dy problem. And the who's on top, who's on bottom, it's who's to the right and who's to the left. And the left is just the axis. And then the boundaries, the limits of integration, it's from where to where on the y-axis. What's the antiderivative of 1 over y? It is natural log y. It's natural log absolute value y, but these are both positive, so I can dispense with that formality. So that's natural log e minus natural log 1, which is 1. All right, just a couple more left. Number 15, we've got the curves y equals 2 over 1 plus x squared. Just looking at that might make you think about tangent inverse. Maybe that's going to happen. And y equals absolute value of x. What does this look like? Try to leave enough room for a 16 down here. Here, I'll write a 16 so it can protect its territory. If you plug 0 in this, you get 2. If you plug 1 into this, or negative 1, you get 1. And then when you start to plug things bigger than 1 in, you start to get things bigger than 2, so it comes down. It's never going to get negative, but as the bottom explodes, it's going to get asymptotic to the axis. And absolute value function, you know what that looks like. And it goes through the points 1, 1, and 1, negative 1, 1. So it looks like we're talking about this area. Now I'm going to do, since I don't really want to deal with that absolute value sign if I don't have to, this is just the line y equals x right here. And this area, this thing's symmetric. These are both even functions. So I'm just going to find that area and double it. So my area is 2 times the integral from 0 to 1. Who's on top? That. Minus who's on the bottom. This is just y equals x when we're on this side, dx. If you were going to do both, you can't. We don't have rules for finding antiderivatives or derivatives of things inside absolute value functions, so you'd have to break it up anyway. And I'm just recognizing that breaking it up, I'm going to get another thing that has the same area. All right, so let's see. That's 2 times this, the antiderivative, that's just a constant, so that's 2 tangent inverse x minus x squared over 2 from 0 to 1. And I guess I'll just leave the 2 out there and deal with that one in there. So what's the tangent inverse of 1? Well, that's the same as saying what angle has a tangent of 1. That's pi over 4. So 2 times pi over 4 is pi over 2 minus 1 squared over 2 minus, what's the tangent inverse of 0? It's 0. And then what's 0 to, I guess that's just a whole bunch of 0 there. So 2 times that, that looks like pi minus 1 is our area. All right. Last one, number 16. I have y equals 1 over the square root of 1 minus that. Hey, that's the derivative of sine inverse. How about that? What does it look like? Well, let's see. We can kind of puzzle through it the same way we did with this. I'm sure we can figure it out. It can be negative. And you're not going to be plugging in numbers bigger than 1 or -1, because that would make this undefined. So it's not defined on those, which makes sense because the sine function, a sine inverse, is not defined outside of -1 to 1. So that's fine. All right, so what if I plugged in 0? If I plug in 0 here, I get 1. If I plug in like 1/2, then I would get 1 over the square root of 1/2, which is the same as the square root. Just make sure I'm not going to tell you something wrong. If I plug in 1/2, 1/2 squared is 1/4. 1 minus 1/4 is 1 minus 1/4 is 3/4, so that would give me 1 over the square root of 3/4, which is the same as dividing by a fraction, same as multiplying by the reciprocal. That's 2 over the square root of 3. So is this helpful for us? I guess. So that's here. So somehow, where are we going from? Y equals 2 is the other thing. So what I should be doing here is setting that equal to 2. So I can figure out where, that's 1, y equals 2, where it intersects that. That's what I should be doing, instead of trying to make a sketch of the whole thing. So this looks like some kind of, almost like a secant function, I think, piece of. So when y equals 2, then this must equal 1/2. So 1 minus x squared is equal to 1/4, so x squared is equal to 3/4. So x is equal to plus or minus the square root of 3 over 2. Okay? So whatever this looks like, those are the intersection points. So I need to go from the integral from negative square root of 3 over 2 to positive square root of 3 over 2 of, what's on top is the 2, right? And what's on the bottom is this. Okay? Antiderivative of 2 is 2x. The antiderivative of this is sine inverse of x. And, well, that's all right. I've got some pretty nice numbers here for the sine inverse function, don't I? So 2 times square root of 3 over 2 is just the square root of 3, minus the sine inverse of the square root of 3 over 2 is pi over 6. Minus, by the symmetry of this thing, we're probably just going to get, we are going to get just double of this, but let's go ahead and do it anyway. So minus square root of 3 over 2 times 2. Oh, maybe not. Wait. Oh, sorry, I'm putting in minus. There we go, yeah. So minus square root of 3. And then the minus, the sine inverse of negative square root of 3 over 2 is negative pi over 6. So I just get the doubling of this. So that is 2 square root of 3 minus pi over 3. That's pretty tricky, that one. But you know what? The sine inverse of square root of 3 over 2 is not pi over 6. That's the sine inverse of 1/2. It's pi over 3. Sorry about that. And that means I got 2 pi over 3. There we go. All right.